Okay, so we'll continue our conversation on cohomology. So let me just remind you how we build up cohomology. If you have some topological space X, we can talk about the homology of the space by first describing the chain complex. So this is just a bit of review where you have your chain complex, and we can have different kinds of chain complexes based on if we're doing simplicial or cellular or singular homology, but whatever your chain complex here is, these chains are abelian groups. And we have these boundary maps from one chain to the next, where I can put subscripts to indicate where the boundary maps are mapping from. And then we define homology. So homology to be Hn of your chain complex. So this is actually the homology of a chain complex, but your chain complex can derive from some space. Your homology of the chain complex is just going to be the kernel of, if you're thinking of like C2, it would be the kernel of this map. In general, for Hn, it would be the kernel of the nth boundary map over the image of the previous map, right? Over the image of n plus 1. These maps are homomorphisms, and the homomorphisms between abelian groups. So this is well defined. Okay, so that's how we define homology. To get cohomology, we dualize by looking at all of the homomorphisms from your chain complex into some ring. We've been using Z, but you could also do Z sub 2 or Z sub 5 or Q, whatever guy you want. I'll just do Z here for simplicity. And so dualizing, we look at the homomorphisms from C0 to Z, the homomorphisms from C1 to Z, the homomorphisms from C2 to Z, the homomorphisms from C3 to Z, and so forth. This would still be 0. Homomorphism from 0 to Z is still 0. And note, we commented last time on how when you dualize, these arrows get reversed. So we'll now call these boundary maps, I'll denote them with the symbol delta for these boundary maps. But I'll stick with the numbering. So this here is delta 1, this is delta 0, this is delta 2, this is delta 3, this is delta 4. So here it was delta 2 saying it was mapping from C2 to C1. And here boundary 2 is mapping from C2 to C1. Here delta 2 is mapping from hom of C1 to homs of C2, right? So now these, for shorthand, I'll often just denote this C upper 0, C upper 1, C upper 2, C upper 3 to denote the dualizations. And then we define for cohomology we get that H upper n, the cohomology, nth cohomology group of your chain complex is going to be, well, now we have to be a little bit careful in how we do this. If this is like my n, if my n is 2, I want the kernel of this map, so it would be the kernel of 3, in general the kernel of delta n plus 1, over the image of this map, over the image of delta n. So note here it was n and n plus 1 on bottom. Here it's n plus 1 on top and n on bottom because we had reversed the arrows. So keep that in mind. Okay, that's how we define cohomology. Last time we noted there's a relationship between homology and cohomology. That the nth, so if these guys are finitely generated, so little asterisks, but if these are finitely generated, all the examples we're doing, these are finitely generated abelian groups, then the nth homology group of C with Z coefficients. I should emphasize here, I was using Z coefficients because we dualized with Z. If you dualize with something else, maybe Z2, this would be Z2 coefficients. Here I did it with z coefficients. If you do have z coefficients, this just comes out to be the same thing as the nth homology group of your chain complex, modded out by the torsion of that group. So this would be like modding out by any z2, z3, anything like that. And then direct summing with the torsion of the previous group. And I gave some examples of this in the last lecture, so you can go back and see that. What this means, though, is if you have no torsion, if you just have like free pieces, like all your homology is like z to the 2, z cubed, and so forth, you don't have any z sub 2z, no z sub 3c, etc., then there's nothing here to mod out by or direct sum with, and the homology and the cohomology is the same, right? So in the case of a torus, the homology groups of a torus are, well, I mean, we can just do them all at once. Hn of the torus, do you recall what it is? It's z for 0 and 2, but in the case of n equals 1, it's z squared. You have two generators of your torus. In the case of H1, one is like this guy, call him alpha, and one, or call him A, and one is like this guy, call him B, right? Okay. And then finally here, 0 otherwise. And what this tells us is that your cohomology is going to be the exact same, right? So your cohomology, Hn of the torus with z coefficients, will be the exact same. If you have some other coefficients, this doesn't quite hold. Instead, we have this universal coefficient theorem, where it gets a little bit more complicated, right? But with z coefficients, it turns out that the cohomology and the homology of the torus are the same. And so this led us last time to reflect a little bit like what is homology good for, or cohomology good for? Like what is cohomology introducing that homology doesn't already have? If you can define your cohomology in terms of your homology, what new things do we get from cohomology? And so the new thing we're going to get is what I want to talk about today, and that's called the cup product, which will have the effect of having a ring structure on not just one group, but all of the cohomology groups put together form this kind of ring structure. So let me explain what this cup product is. What a cup product will be is it will be a way of, so our ultimate goal, so here's our big goal, is I want to define this cup map that will take things in the, I should use consistent notation, let's say kth and jth cohomology groups. So this can be some chain complex with, say, z coefficient. It doesn't have to be z coefficients, though. So you can do whatever ring you like. I'll typically use z. If we have time left, I'll do an example of z2 as well. So whatever your coefficients are, and here whatever your coefficients are, I want to be able to take some representative of this cohomology group and of this cohomology group and get out a representative of the kth plus jth cohomology group, right? So we don't have anything like this on homology. There's no way to like combine this A and this B and somehow get something that's in the H2 of the homology of the torus. But we will see there's a way to combine the corresponding cohomology elements, so something that corresponds to this A and this B in cohomology, and get out something in like the H2 cohomology group. So that's what we're going to see today. So I'll come back and do it with the torus in a few minutes, but first let me build up this general theory. Okay, so how can we possibly define a map like this? Well, let's think what h to the k is. We said that your homology is the kernel of this map, and so the kernel of that map is homomorphisms from, in general, Cn to Z. And so if I'm in here, I'm some element of C to the n. So if I'm in here, I can think I have some phi, say, that's in CK of whatever your chain complex is. Let's say this is the chain complex that corresponds to some space. So you have some space X. So we have some space X and co-chain complex C that corresponds to X. So you have phi in here. And I'm just going to do everything with Z coefficients. But the same story holds for other rings. But I'm going to get tired of putting R every time. So I'm just going to tell the story in Z coefficients. But if you prefer, in your mind, change this to Z2 or whatever you want to. So let's just tell the story of Z coefficients. So I have phi in some CK, and I have some other element in here. So let's call him psi in the jth cochain group, so X, Z. And let's think about what these guys are, right? So what this is this is homomorphisms from C sub k to Z. So if you're in something like simplicial, like let's say we built up the chain complex using simplicial homology, then you can think what this is. So this is homomorphisms from CK to Z. And what is CK? CK is some simplex. CK is a K simplex, right? So you start out with some K simplex. I'll call it some sigma K, which is a map, recall, from, I'm sorry, a K simplex is some sigma, I'll call it sigma K, which is a map from a K simplex into your space X, right? So a homomorphism is eating these guys. A homomorphism is a map F that eats in simplicial maps, right? Cool. So this is a K simplex. This guy here is some simplex. So you have some vertices V0 through VK. So we just need to unpack what everything here is. So when I pick phi is a map on sigma k, right? So you're going to be thinking your phi eats in things like sigma k. And it spits out integers. It spits out some integer, right? Just clear on what this guy is. And over here, psi is the same thing. You can think of psi as these are homomorphisms from Cj to Z. So what is Cj? Well, Cj comprises not just these simplicial maps, also linear combinations of simplicial maps, but it's comprised, linear combinations of simplicial maps, sigma j, which is a map from some j simplex into your space X. So what psi is going to do is psi should eat these kinds of simplicial maps. So when I'm describing this should be psi. So when I'm describing my phi and my psi, I should be describing this should eat something that is itself a map on a K simplex, and this should eat something that is itself a map on a J simplex. Okay, is that good? Understand what V and psi are? Because now what I want to do is I want to define this cup product. So I want to define what is phi cup psi. So let's think, what should phi cup psi be? Well, now he's in here. So that's going to be homomorphisms so you can think this is represented by something that corresponds to homomorphism from C of j plus k. So this guy should eat some map, sigma, where the sigma here is a map from a k plus j complex into X. Good? Okay, so I need to define what this is. And I want to define this in terms of what my phi and my psi are, because I already know what these things are. And so here's how I'm going to define it. This k plus j simplex you can think of as just being made up of your vertices, v0 through vk plus j. Note that means there's actually k plus j plus 1 vertices, because you start off at 0. And so what this is going to do is this is going to just be defined to be phi of sigma restricted to, phi can only eat things that have k plus 1 vertices. So what this sigma is going to do is just be sigma restricted to v0 through vk. And then times, this is an integer, times psi of this sigma, now restricted to the remaining vertices. So begin at vk and go through vk plus l. K plus, did I use j or l? I used j, okay, let's be consistent. Well, that was dumb. Why would I put j after k? Okay, well, you gotta live with it now. So this might seem quite bizarre, but let's make it very concrete. So let's have as an example, let's just think on the level of simplexes. So let's say I have some sigmas. I want this phi and this psi to somehow be maps on these sigmas that are acting on one simplices. And so I'm going to think of it as something like this. Let's say I have a 2 simplex. And I'll give this some orientation. Okay, so we can name these vertices if you want to, like v0, v1, v2, and our convention was that we point in the direction of the larger arrow. We talked about this a long time ago. That was just a convention we introduced. So our arrows point to the larger subscript. And what you could think is maybe you have on v0, v1, this here is itself a 1 simplex. v0, v1 is 1 simplex. So let me call this 1 simplex like A. And let me call this 1 simplex B. And let me call this 1 simplex C. Okay? So we just have some 1 simplices that make this up. So A, B, and C is itself the simplex. So now I gotta define like what sigma is. Well, okay, sigma can just be like the inclusion of A into the space X. So let's say this is my space X. So there's what my sigmas are doing. But let's think about what my phis could possibly be. So here's how I'm going to define a couple of phis. And this example will motivate some work we'll do later. I'm going to define alpha, beta, gamma to be elements of, I'm going to think of them, secretly they're elements of H1, but they're represented by these guys in C1. But you can think of them as guys in H1. These are representatives of elements in H1 of X. Okay, I'm not actually calculating homology right now. I don't want to actually calculate homology, so maybe I should just say these are guys in C1. So what these guys should be homomorphisms from this chain complex into Z. And so I'm going to define these homomorphisms in some really natural way, where I'm going to define alpha of A is 1, and alpha of the other guys are 0. And beta of A is 0, but beta of B is 1. So these are like the duals to these guys. Okay, this is kind of a contrived example, but we're going to see something very much like this actually arises here in a couple of minutes. What I just want to make the point of, so gamma of beta, gamma of b is 0, and gamma of c is 1. What I just want to make the point of is once you have some guys like this, alpha, beta, gamma, if I want to calculate, well, what is alpha cup beta of, let me give this region here, this 2 simplex a name, let me call this 2 simplex like R or something for region. What is alpha cup beta of this 2 simplex? This definition is just saying that would be, so my R, maybe I don't even call it R. Maybe it'd be easier if I just call the 2 simplex, the simplex V0, V1, V2. Is that easy? You understand what I'm saying? It's this whole thing. V0, V1, V2. That 2 simplex. What will that come out to be? This will just be alpha of V0, V1, which is A, times beta of V1, V2, which is B, which is 1 times 1, so it comes out to be 1. However, if I did something like, well, what is beta cup gamma of V0, V1, V2, you tell me, what is that going to come out to be? It would be beta of V0, V1, which is A, times gamma of V1, V2, which is B, and that would just come out to be 0, right? Is it clear how this works? Are we happy? Okay. Maybe one last observation. Can you tell me what is beta cup alpha of the simplex of V0, V1, V2? Yeah, so this also comes out to be 0. So this is kind of strange, right? Like, this isn't commutative. Okay. Okay. So we will, so that's what I mean by this definition. And you can do bigger things too, right? If you instead had, should I do a higher dimensional example, or is this clear from the definition how you would do that? If you wanted to have like a 1 simplex and a 2 simplex, you can combine those to get a 3 simplex. Should I do something? This is going to be, let's see some more examples here in a second. I don't want to get lost in these little examples. Okay, so we've defined this cup product. What I want to do now is I want to think about, so let me circle this, like emphasize, like this is my definition. This is the definition of my cup product. What I want to do now is I want to think about how does boundary play with the cup product. So here, my boundary map is going to be some map from Cn of xz to Cn plus 1 of xz. But what I want you to remember is, what did we say last time the boundary of something in here like alpha is going to come out to be? Yeah, the boundary of alpha is just alpha composed with the boundary, right? So let's unpack what that means for our cup product. So for our cup product, so what do I really mean by this? So say alpha is in here. So alpha is in here. So that means this guy should be eating some sigma n. Well, I'll use the subscript n to denote that this is a map on an n. This is an n simplicial map, a map on an n simplex. What should he be over here now? We're like, alpha eats, oh no, alpha eats an n simplicial map. But the boundary of alpha should be eating the boundary of alpha, this should be mapped over here. The boundary of alpha should be something over here. So the boundary of alpha should be eating an n plus 1 simplicial map. So the boundary of alpha should be eating an n plus 1 simplicial map. And like, how can he be eating an n plus 1 simplicial map? And then you say, well, the way he's eating an n plus 1 simplicial map is he's just alpha applied to the boundary of the n plus 1 simplicial map, because the boundary of an n plus 1 simplicial map will become an n simplicial map. Right? Cool. So that's how, by composing the opposite order, this becomes well-defined. Okay, so let's think so with that in view, let's think what is the boundary of a cup product. Okay, so we got to be careful here. So let's say, just as before, I'm going to keep this notation. I'm in K and J, so I'm in K plus J. So what kind of guy should he be eating? So this you can think of as an H of upper K plus J. So the boundary of it should be K plus J plus 1, right? So it's like, how could this be? So you're thinking like this guy here is some map. This is a map, K plus J plus 1. A map from V0 through V, K plus J plus 1 into whatever your space is, right? So like, how are we going to define this? And well, we've already given it away. This is just going to be the cup product of the boundary of this guy. But what is the boundary of this guy? Do you recall how we defined the boundary of these things? Alternating sum. This is just going to be V cup psi of the alternating sum. So the sum from I equals 1 to K plus J plus 1 of I equals 0, thank you, of negative 1 to the I of sigma restricted to, and what you do is you just each time remove one of the vertices. So this is going to be V0, omit the V'th guy, and then at the end, okay, we ran out of room. K plus J plus 1. Okay, just omitting the ith character. But everything here is homomorphisms. So it's linear. So this should be the same thing as the alternating sum minus 1 to the I of just phi cup psi of my, I want a shorthand notation. If I just put, I should write it all. V0 omitting Vi going through Vk plus J plus 1, where I goes from 0 to J plus K plus 1. Okay, that's the boundary of this guy. This might look really messy, right? Like, what can we do with this? What I claim, and we'll see if we have time, we can show it quickly. What I claim is that this comes out to just be the same thing as, well, it's kind of like a product rule from calculus. It will come out to be just the boundary of phi cup psi plus the boundary, plus phi cup the boundary of C. Right, so that's what I'm going to show. Except you might possibly get a factor of -1 depending on the dimension of psi. So here I said my psi was j, so it'd be -1 to the j. So this is what I want to show. So we're at a board space But I can show this. I'll just erase, and I think I can show it right here. So let's show this really fast. So let me calculate those two terms on the right, and then I'll argue those two terms on the right are equally the same as this guy, right? OK. So the first term on the right is the boundary of phi cup psi. So what does this come out to be? And so that's going to be eating in some again, that's also a sigma. This is also eating in some sigma of j of k plus j plus 1. Right? Because this is going to be a k plus 1 and this is a j. Right? So this is the correct guy. So what does this come out to be? Well, the definition of your cup product is that this should just be the boundary of phi of sigma restricted to k plus 1. So v0 through vk plus 1 times psi of sigma restricted to the remaining guys. So v0 through, oh, nope, starting now at k plus 1, vk plus 1 through vk plus j plus 1. OK, so that's what this is equal to, right? And then this guy right here is just going to, you can bring this inside like we did before. And so let's try and skip a few steps. That'll just make it the alternating sum of this. So you end up with the alternating sum of -1 to the I, where I goes from 0 to k plus 1 to k plus 1 of phi of sigma restricted to v0 through, omit the ith term, vk plus 1, that whole thing times the sigma, times sigma of psi of sigma restricted from vk plus 1 down through vk plus j plus 1. Good? But that is exactly, when you apply this cup product to this, it's exactly the first term. If you do, well, when you do this, you're going to have phi of this guy times psi of the remaining pieces. And when you're doing i's equal from 0 to k plus 1, you get exactly this. Is that clear? Do I need to unpack this definition more? It's just going to be phi of the first, well, it would typically be the first k, but since you're omitting 1, it goes up through k plus 1. And then psi would pick up a k plus 1 and go through here. So this matches exactly this guy for all of the terms 0 through k plus 1. Now, for the rest of the terms, let's just think about, so I claim the rest of the terms should come from this other guy. So what is phi cup, the boundary of psi of this guy, of sigma of k plus j plus 1? Well, that's just going to be equal to phi of sigma of v0 through vk plus 1 times psi times the boundary of psi of this guy. So just like above, you can move the boundary inside. So it's times the alternating sum of I equals 0 to, well, we'll think in a second what you end up here, because when you move this inside, it's -1 to this power I of psi of sigma, but your sigma has now been restricted from vk plus 1 down through vk plus j plus 1, where the ith term, I've got to omit the ith term, where the ith term has been omitted. Huh? Oh, well, here I'm just going to treat I as going from, say, k plus 1 through k plus j plus 1, and that will solve that problem. Okay.
Shouldn't phi start go from v0 to vk since phi is a vk?
Yes, yes, yes. He should go from to vk, so he should start off at vk. That's right. So this should start at k, which is exactly why you have to multiply by this I to the -1 to the, but that's j. Let's check indexing. So what's going to happen here is I claim these correspond to here once the index gets to k plus 1. You're omitting the k plus 1 term. Because here, the first one you omit is k, which means you're starting off at k plus 1. Oh, what went wrong here? This was good. That should be up to k. And this is good. And so I start off omitting at k. And if I omit at k, he goes up through k, and he starts off at k plus 1. Whereas here, if I omit the k plus 1, I would have up to k. But then he would be k through. So something's off here. Arg. It's just an indexing thing where we have to like think through these indexes carefully. This is correct. That's correct.
I'm checking the book and it is the dimension of the first one, so the formula on the right is wrong.
The formula on the right's wrong.
Yeah, it should be k.
What should be k?
The j.
No minus.
Where?
The negative 1 to the j should be the negative 1.
In your claim.
Right here?
Red box.
Oh, this is k. That is k?
That is k.
Oh, it's the dimension of the first one. Because I have flipped j and k in this example where j usually comes before k. So j usually comes before k. But in this example, k is the dimension of the first one, j is the example of the second one. And so that's why you get this I to the k, -1 to the k factor. Okay, so work through this, double check this, but hopefully this convinces you of the spirit of it. There's some indexing you have to be careful about, but there you go. There's the property of how the boundary map plays with this. What I really want to do, though, is think through the implications of this. In particular, I claim that from here, that means we have a map, that we have this map, that it induces this map. And so in order to see that, let's just think clearly about what this would really, how do we know this map's well-defined? So I claim that this boundary criteria can show us that this map is well-defined, so that this U is well-defined. So I claim that U here from H, K, from C, we'll just do Z coefficients, but we can do other coefficients as well, to J. Why am I doing J there? It doesn't make any sense. To Z, all the way to the right of H, K plus J of C R, which now I've committed to being Z, I claim this is well-defined. So let's think about what this claim is. So in order for this to be well-defined, I need to have, what is HK? HK is the kernel, come back over here, it's the kernel of the k plus 1 delta boundary map over the image of the kth one cross Hj, likewise, is the kernel of j plus 1 over the image of the jth boundary map. And that should be assigned to some map on the kernel of the kth plus jth plus 1 boundary map over the image of the kth plus jth. K plus jth. Each one of these, so things in the kernel and things in the image, if you're in the kernel, we call it a cocycle, because the idea is a cycle has no boundary. A cycle would take the boundary, but it goes to 0. And we're in cohomology, so it's the analogy of that. So this is just cocycles over everything in the image is itself the boundary of something, so over co-boundaries. Right, so that was my language, cycles and boundaries for kernels and image, and now it's just cocycles and co-boundaries. And so what I want to show is if I pick something here that happens to be in the image, so it's like it's 0 here, it's modded out, it will also be in the image here. That's what I want to show, right? Or if I pick something here that's 0, it will also be 0 over here. Okay? So from the construction, we already have that things in this kernel times things in this kernel go to things in this kernel. Is that clear? Like if you're in this kernel and you're this kernel, you go to. But now I want to show that if you're in the image, you still remain 0. You still remain in the image. And I claim that follows directly from this property. So let's think. So there are two cases here. One case is suppose my phi. So one case is that your phi might be in the image of this guy. So you could write phi as like the boundary of some, I don't know, I'll call it alpha. Let's think what that tells us then. Looking at this property right here, you would get that the boundary of phi with psi is equal to the boundary of phi cup psi plus or minus, depending on what your sign is, what your dimension is, phi cup the boundary of psi. But notice right here, if phi is itself in the image, then this would be the boundary of alpha. So that's going to be 0, right? So that is just going to die. And so you get that if you were in if your phi is in the image, then phi union psi gets mapped to phi union the boundary of psi. And likewise, if your psi is in this image here, then you can think of the psi as being like the boundary of some beta or something. But you would get something exactly analogous. This guy would just die. So you would just have that the boundary of phi union psi is the boundary of phi union psi. Great. So what this is saying is the cup product of a cocycle with a coboundary comes out to be a coboundary. And same thing here, this cup product of this coboundary with this cocycle comes out to be a co-boundary. So if either one of the guys is a co-boundary, then the resulting cup product will also be a co-boundary. Yep. Okay, cool. So well defined. Okay, so I had wanted to end today by calculating the cup product of a couple examples. But realistically, we could spend a whole lecture just doing cup products. And so I think what I'll do today is stop here and say, we've defined the cup product. It was messy, and this is a little bit abstract. But next lecture, I'll just do a bunch of examples. And so hopefully I'll make it very concrete. We'll see how the cup product of like a torus or Klein bottle, we'll go through a couple different spaces, and hopefully I'll give you a very clear idea of how cup product works. So next week should be a lot more concrete, and we're actually going to calculate things. But now we know, how the cup product works. So next week we'll just pick up from this definition and start calculating a bunch of examples. So we'll stop there.